Welcome to The Explainer. Today, we're diving into a genuinely mind-bending new hypothesis about the fundamental building blocks of our entire universe. We're going to be looking at a fascinating paper by researcher, inventor, and author Kevin L. Brown. He's proposing a totally new way to think about one of the most common particles in existence, the electron. It's called the electron identity field recursion hypothesis. Sounds intense, right? But don't worry, we're going to break it all down simply. Let's dive in and see how this might literally change the way we look at reality itself. So here's our roadmap for today. We'll start with the electron mystery, move into the revised hypothesis, look at testing structural pressure, discuss how to prove it wrong, and finally wrap up with the real-world quantum impacts.
All right, part 1, the electron mystery, a universal baseline.
So, I want to pose a fundamental question to you right off the bat. What exactly is an electron? If you zoom all the way down into the atoms making up your body, or the device you're watching this on right now, or even the stars up in the sky, you're going to find electrons. But there's a really strange mystery about them that has puzzled scientists for decades. You see, every single electron in the universe is exactly, completely identical to every other electron. I mean, they have the exact same mass, the exact same charge, and the exact same spin. But why? Why are they all perfect clones?
While standard quantum electrodynamics, or QED for short, is our current baseline theory. It's fantastic at explaining how these particles behave, but it fundamentally treats them as separate, independent objects. Imagine a giant factory stamping out trillions of identical coins. QED perfectly explains how those coins act once they're minted, but it doesn't really deeply explain why there is absolutely zero variation between them across the entire universe. It just treats them as separate little objects that happen to share a perfect identical list of properties.
Which brings us to part 2, the revised hypothesis, a brilliant shift.
Let's look at this concept directly from Kevin L. Brown. He states, one electron identity architecture leads to one fermiotic field family, which leads to many locally bounded excitations. Okay, what does that actually mean for us? In simpler terms, instead of electrons being completely separate objects zooming around, they're more like temporary waves popping up from one single shared ocean. Now, just to be clear, years ago, famous physicists like John Wheeler wondered if all electrons were literally just one single particle traveling backward and forward in time everywhere at once. But Brown's structurally revised hypothesis is not saying that. Instead, he's suggesting a much more testable idea. He's saying there is one universal architecture, kind of like a single master blueprint for every electron.
And there's a really great way to illustrate this difference. Under the standard QAD view, you see electrons as separate, completely unrelated clones. But under Brown's electron identity field recursion hypothesis, or EIFRH, electrons are local projections drawn from one universal blueprint. Think of it like a video game. When you see 10 identical trees in a game world, the computer's memory doesn't hold 10 completely separate, unrelated tree files. No, it holds one master rulebook for tree and just projects it 10 times locally in your game. Brown's hypothesis argues that electrons do exactly this. They preserve a single, recursively stable identity architecture.
Moving right along to part 3, structural pressure, validation testing.
Now, any theory is really only as good as its validation test, right? Well, Kevin L. Brown proposes testing his idea by looking for something he calls structural pressure. So what is that? Basically, it's a measurable buildup that happens when a confined electron is driven through repeated, phase-locked transformations. I know that sounds like a mouthful, but it basically just means putting the electron through a very precise repeating rhythm. If an electron truly is just a local projection of a universal blueprint, you should be able to stress test its connection to that blueprint. Let's walk through the simple 1-2-3 flow of how this experiment would actually work in the real world. Step 1. You trap a single electron in a highly controlled environment, like a magnetic device called a penning trap. Step 2. You apply a very specific, repeating rhythm of energy to it. This is a cycle of preparing it, driving it, and reading it out. And Step 3. You measure the resulting structural pressure. You're basically repeating a sequence over and over again really rapidly just to see if a measurable pressure builds up on that electron, something that standard physics cannot explain.
As you repeatedly drive the electron, imagine this structural pressure rising higher and higher, approaching what we call a critical threshold, or PC. The hypothesis predicts that if this pressure hits that specific limit, the system is going to show a visible physical change. The electron might suddenly jump out of its expected rhythm, or maybe show a tiny shift in its phase that standard QED simply did not predict. And if we actually detect that shift, it strongly suggests the electron is deeply, fundamentally connected to that universal architecture Brown described. It would be an absolute game changer.
All right, part 4,
proving it wrong, falsification parameters.
You know, true science must absolutely be falsifiable. That means a researcher has to be brave enough to say, hey, if you see X, Y, or Z happen in the lab, my theory is totally incorrect. And Kevin L. Brown does exactly this by outlining very strict falsification parameters.
Here are the exact conditions that would completely disprove his hypothesis. First, the primary null result. If the experiment reaches its absolute highest sensitivity and finds zero structural pressure buildup, the hypothesis is false. Second, if the pressure doesn't grow in a predictable 1 to 2 to 3 pattern as the cycles increase, it's false. Third, if you literally flip the experiment upside down, a phase inversion, and it fails to flip the result, false. Fourth, if you apply random noise as a control and get the exact same effect, well, that just means it's a normal error, not a universal blueprint. And lastly, if there's no clear threshold detected at all. So Brown has laid down a highly specific gauntlet here. If his hypothesis survives these tests, we are looking at a massive scientific breakthrough.
Which leads us perfectly to Part 5, Quantum Impacts, Real-World Implications.
So what's the big so what here? Well, if Kevin L. Brown's model is validated, the real-world implications are huge, especially in the engineering and application layer. Right now, major tech companies are in this massive race to build quantum computers. If we learn that electrons genuinely have this measurable structural pressure, engineers can actually use it. We could build much more stable electron spin qubits, which are basically the core processors of quantum computers. It would lead to advanced quantum logic gates, highly precise magnetic sensing devices, and a completely new way to correct errors in quantum computing. Engineers could intentionally keep systems below that critical threshold for ultimate stability, or deliberately push them right over the edge to generate controlled high-tech transitions. It literally upgrades our entire toolkit for microscopic technology.
I want to leave you with this final provocative thought. For decades, whenever physics hit a wall, scientists just built bigger and bigger colliders to smash things together, hoping to find brand new, mysterious particles. But Kevin L. Brown's work asks us a completely different question. Is the strongest search location in physics not a new particle, but a missing interaction between the ones we already have? Maybe the greatest mysteries of our universe aren't hiding in some undiscovered matter, but in a universal architecture that has been right in front of us inside every single electron the entire time. It really makes you wonder what else we might be missing just because we're so used to how things look. Thanks for joining me on this explainer, and keep questioning the universe.